later than ever before. I'm coming to this week. I'm back from Morocco, and let's go on. So the difference equations or linear recurrences, what we shall be dealing with is what you see on the screen. The definition is easy. So what we look at is we've got something like a unknown infinite vector of values x0, x1 and so on up to xk and so on. That goes to infinity, and what we have got is a definition how the nth value is dependent on the k previous ones, and that's something what we call a difference equation of order k. We saw them in the first week already a little bit. So of course we work now over fields of scalars, so a0 is non-zero, and so we can divide by that and compute. So we see that really it's what I told. So xn is some function of n, so valued at n, and we define the function by telling what the fn would be, knowing the k previous values. So that's it. So right. So in the definition here, although it doesn't look like that, so we do not exclude that the a0 up to ak will depend on the n we are at. So we define the n's value, so the coefficients might be dependent on the n we are currently dealing with, of course. But if we want to go for something more handy, then very often also in the practical cases we have simply situation where the values are all the time constant. So for example, we have a second order recurrence formula which could be thought as a population model. So you can imagine that the species we are talking about, the animals or whoever, are mature to give the new birth after 2 seasons. So fn plus 2 will be a constant multiple of fn. Perhaps b will be something bigger than 1, positive. There might be some c which will be perhaps either negative if someone is eating or using the population in some way, or it might be positive if you are buying new rabbits, so it will be growing. Every year you just add c of the rabbits into your group. And maybe the not yet mature animals, the kids, are giving a lot of problems, so maybe that there will be some negative a. So taking into care that the population somehow develops also. So that's how it works. So we have seen already one such case with c equals 0. That was the very well-known Fibonacci sequence. And what to do with the general case. So whenever you deal with some mathematics and you should try thinking about how to solve something, how to crack the things, well, one of the options is, if you don't know, just try something which did work in similar cases. So we saw that in the case of the Maltesian growth, we had xn was a times xn minus 1, right? So that was the Maltesian growth, and that immediately just meant that we have got a to power n times x0 equals xn, right? So that's easy. So we are seeking for some constant, let's call it unknown constant lambda, and plug it into our equation. So we have got this equation which was xn plus 2 was axn plus 1 plus bxn plus c, right? So and forget about c for beginning. So there will be a homogeneous case. Well, I didn't tell actually the most important thing. So let me come back. The most important thing is that as long as the rule how to compute the xn from the previous k1s is linear, so it means we have some coefficients times the values, we can see that if we add two solutions, it's again a solution. If we multiply a solution by a constant, it's again a solution. So the goal of ours is now to find out some reasonable number of solutions so that all the others will be obtained by linear combinations, because as I was just telling, all the solutions create a vector space. And how big will the vector space be? So if it's case order difference equation, then perhaps you have k slots to fill in as beginning condition, the initial condition. So it will be a vector of rank k, right? So we have to expect that we need exactly k independent solutions to get all the others by linear combinations. And that's exactly what we shall be heading at, because if you just try to plug in this solution as in the Maltesian model, but of course we don't know now what the lambda could be, and you throw it into the equation, you see that there will be an equation lambda, so it's just you see it here, so it will be the equation. So here we have lambda to n plus 2, here we have lambda plus to n plus 1, and we have lambda to n. So what we end with is a polynomial equation that this very polynomial has to equal to 0. And now we can just write lambda to n in front of the bracket, and you see that it will be exactly a second order polynomial. And we know, although we haven't proved it yet, that every second order polynomial has got exactly two roots, maybe including multiplicities, and the roots are possibly complex. In our case, it will be root number 1, root number 2, right? And we see two solutions. So this is how we can deal with the general ones, and then all the solutions will be linear combinations of those. And of course, C1 and C2 will be computed from the initial conditions. And the initial conditions can be somewhere in the middle. You can say that the hundreds and hundreds first will be of this kind, or any other two, and you can compute it, right? And then you can go backwards and forwards, and you see that you get exactly what we need. There is an interesting feature which we see. So for example, if you take this equation, so A is 1 and B is 1/2, and say we have got some initial conditions. So this is how you solve it. You get the two roots of the polynomial. You know that you have to compute what the C1 and C2 would be, so you do it, and you get the formula for Fn. And the formula looks like a horrible one, right? You see, it's a formula, that's good, but it looks like highly irrational, right? So you have the square roots of 3 there everywhere. But at the same time, you know that starting with initial condition, which is natural, 2 and 0, then all the future values must be rational, right? Because you have this 1/2 there, but computing iteratively the yn plus 1, yn plus 2, and so on, it will always give you a rational number. So in total, you know that the Fn must be rational all the time, and it is, right? So but it shows the fact that often we simply need the extension of the rational numbers in order to be able to compute rationally, right? So effectively. So this is an example of that. Right, and this scheme which we just saw at the second order works in general. So if you have case order linear recurrence with constant coefficients, so you immediately see that the vector space of all the solutions will contain the solutions lambda to the power n for the nth term, and the lambda must be a root of this case ordered polynomial then. And that's quite easy, except we don't know yet what to do with the multiple roots. So if there are multiple roots, there is a very simple thing that if there is a double root, so then one can find out quite easily and straightforward. You can read it in text that if you write xn equals n times lambda n, that it would be a solution, and in general you get exactly the same thing as many times. So xn equals n to l lambda n, where lambda are the complex, possibly roots of the characteristic polynomial, and the powers L goes through 0 to the multiplicity minus 1. So if the multiplicity is just 1, it's only the lambda to n there. If we have multiplicity 3, there will be 2 more, n times lambda n, lambda to n, and n squared times lambda to n. And that's the complete set of the nice solutions. Now, going one step further, you should also just be worried about what to do with the, say, real linear recurrence equations, but having the complex roots for lambda. And then the answer is again easy. So what you do is you write lambda n in the polar form, so the geometric form, and of course you know that if the polynomial, if the coefficients were all real, then the solutions will be always coming in couples of 2 complex conjugate ones. So it's lambda to n and lambda bar to n. Lambda bar to n will be just the second line here, and obviously you see that if you add those two or subtract those two, so what you get finally is 2 lines of solutions. So xn will be coming with cosine of n phi, and yn will be coming with sine n phi, and that's exactly what you have to expect. So the complex roots of the characteristic equation will correspond to some periodicity in the solutions, whereas the real ones will let it grow or decline exponentially. So this is the thing. And what remains to understand roughly the linear recurrences is what to do if it's not homogeneous. So if our equation is not having 0 on the right hand side but some Bn. And again, it's the same story like with linear equations, right? So therefore it's here as a illustration, and the thing is that the necessary step is that we have to guess one of the solutions of the non-homogeneous one, and then we can add all the solutions of the homogeneous one. We shall come up in later semesters, we shall come up with some more fancy and smart approaches how to solve such equations. Here what remains to say is only how to deal with the most simple things, and that's if the right hand side are of some very simple and special kind, like having a polynomial in n there, or just a constant would be a special case of that. Then we know that there will be a polynomial solution, and we can compute which one. So it's described here. Another option is the so-called variation of constants. This is again a quite nice approach, which is more smart, more tricky. So I leave it on you whether you read through or not. The point is that if we find the solution of the homogeneous case, so the general solution, so there will be the k special solutions, so that's what we know will be the exponential ones with the corresponding lambdas, and there are some coefficients here, scalar coefficients, so the general linear combinations give you all the solutions. And now the next step is that you simply say what would happen if we allow the coefficients to depend on n, knowing that the fi's are the solution of the homogeneous case. And you compute what's happening with plugging in these unknown CINs. And the result is that you get something quite fancy, and it allows you to solve, in many cases, the original equation, right? So there is an example showing it in practice. Right, I would like to add with some comments, which are quite, I hope, quite illuminating, and that's another understanding of what's happening when we deal with the linear recurrences. You can also view it in such a way that you actually have got something like say x minus n x0 x1, so a more infinite sequence of numbers from, so it's just for all the integers, right? So we go through, and then you have something like a operation which I call t, and the operation just brings it into something like again a infinite thing, y minus n, y0, y1, yn, and so on, and this is equal, this is simply just given by yn equals t of x, which means the n thing, and this is something like a 1 x n minus 1 plus a 2 and so on. So it will be some case order linear recurrence thing which would be appearing here, right? And the kernel, so you see that this is a linear, this is clearly the t is clearly a linear map, and the kernel of the map is solution to the linear recurrence. So and what we can understand is that the linear map T is something like a filter. So you can imagine that for example the x's are a well, potentially infinite, but in reality finite, but very long vector of, say, audio data sampled by at some frequency. So you have something like 44,000 for each second, or something like that. And there is a linear filter which produces new line of the sampled signal. And if we look what's happening, so for example, in this case, you see immediately that for some frequencies of the signal, this filter will produce exactly the same thing. So that's the condition. Or it will be just multiplied by 2, or it could be just completely suppressed. So it will be 0. There will be the kernel of the t, right? And that's exactly how the very simple linear filter have been done in electrotechnics, say 50 years back. So it was hardwired, and there were some loops doing exactly this. And you can observe when looking more carefully what's the drawback of this kind of linear filtering. So it looks great, so such a simple thing, and you can suppress some frequencies and multiply others and kill some of them completely. You can combine it so you can get the equalizer as you know it. And the problem is that for each frequency the phase will be shifted in a different way, and that's something our ear is sensitive at, because the change of the phases corresponds to the sound coming from different directions. So you have two ears, and coming from direction means that one of the ears gets it later than the other, and so you can guess from which side it comes by that, among others, right? And so this is the reason why the cheap equalizers completely damage the sound, so it sounds strange. Right, that's the end of the linear recurrences for this week.